So it might be a dumb way to think about it, but I guess with that, guess I'll use this diagram that you.
Yeah, sure.
It feels a little too small though, so guess
go ahead.
I'll draw something a little bigger. So, for example, a vector field similar to the one that you just drew, versus a vector field with just a point charge. With all these arrows pointing outwards. So I guess this might be a dumb way of going about it, but I guess if you have that point where the vector is originating from, then the position vector then has a very large angle with the vector field at that point, while and with this point charge, the position vector is in the same direction as the vector field. I don't know, that's just my way of looking at it.
Yeah. Yeah, actually, I would say that's not a bad way.
Well, I don't understand curl that much, so me and a tutor from my relativity class, Giovanni, we're just going to go over a few definitions from vector calculus together so that we can get a better look at Maxwell's equations and how they apply to relativity. Can I summarize it good enough?
Yeah.
Okay, great.
So, you remember from linear algebra and probably maybe even vector calculus that the way we multiply vectors is there's the dot product for two vectors, and this is a scalar operation, so it's a real number, and then there's the cross product, and this is a vector as well. And the way we define the cross product, of course, we can only use the three-dimensional case because that's the only.
It's the determinant of that matrix, right?
Yes. So we define V cross W as this determinant where we put the basis vectors in Euclidean space in this top row, and then the first vector goes in the second. So I'll use V1, V2, 3, W1, W2, W3. And then of course this I'm going to write it in column vector notation. I don't know what convention you use, but I always like to cross out the first row and second column and then take the determinant here for each one. So this would be V2, W3, minus V3, W2. And then for the second one, we have this negative sign when we do that same thing. So it's V1, or the negative of the quantity V1, W3, minus W1, V3. And then for the last one, of course, we have V1, W2, minus V2, W1. So this is a vector, and if we wanted to plot in Euclidean space, what this looks like is, and I'll use a different color.
It's the vector that's perpendicular to both of the
Exactly,
W, right?
yes. So maybe this is V and this is W. Its curl would look, or its cross product would look something like this. Now, for going back to vector calculus now, the curl is defined as nabla cross whatever vector function you're looking at, maybe f here. So it's kind of bad notation, but just to remind ourselves. But
wait, would this be partial xf or?
No, this is just the regular nabla symbol.
Oh,
so
sorry.
No, it's okay. So when we take the curl, we're treating both of these objects as a vector, because this is going to be this is itself a vector as well. So it's going to be this determinant again, and we're going to keep the basis vectors in the top row. I'm actually going to use x hat, y hat, and z hat now, just to kind of assert our Cartesian basis. And then we take the first vector and put its components in here. So in this case, it's going to be partial x, partial y, partial z, and then we'll take fx, fy, fz. So this is going to be this vector here, where it's exactly like the cross product when you compute it. So it'll be partial fc, partial y, minus partial fy partial z, and then we'll have this negative sign here for the center. So it'll be partial fz partial x minus partial fx partial z, and then for the last one, we'll have partial fy partial x minus partial fx partial y. And you can see that, of course, each respective component, so let's say that this is now some other vector, call it g, with these components, gx, gy, and gz correspond to derivatives and components from f that are different than the direction you're in. And that's important because when in covariant notation, we use the Levi-Civita symbol to define, without using these operations, just indices, the curl, or any cross product really. So remember that this, it's +1 for positive permutations of the indices. I'll denote it as perm of 1, 2, 3. -1 for, even permutations of 1, 2, 3, and then odd permutations corresponds to -1, and then 0 otherwise. And the otherwise means, in the case of 3 indices, yes, exactly. So, just an example, 1, 2, 3 is an even permutation, 2, 3, 1, 3, 1, 2. These are all even permutations because it preserves the order of going from 1, 2 to 3. And then for the odd one, 3, 2, 1, 2, 1, 3, and 1, 3, 2 are all odd permutations. So for 2 vectors in general, let's label it I'll use Latin indices here, AI and BJ, where they have, these are column vectors. Another indices are their components like this, lowercase letters, B1, B2, B3. Their cross product, and I'm going to use the hat symbol here and then put the indices on the end. This would be K. This is going to be the Levi-Civita symbol, IJK, A, I, B, J. And hopefully you can kind of see what's going on here. The reason the K is here is because when we do the sum for each component, we're summing over the I's and the J's. So if we wanted to write out, let's say, A cross B, its first component, it would be, so we have epsilon J1, because we've chosen our K value, and then it'll be A, I, B, J. And so now we sum over repeated indices. That's the Einstein summation convention. So what I like to do when I do this is, I know that whatever I choose for this I has to be the same here and the same for this J. So there's going to be 2 different sums here. There's going to be epsilon 1, J1, A1, B, J. Where now we're going to sum over every possible value of J. And of course, our vectors are defined in R3, 3-dimensional space. So these indices can only go from 1 to 3. So
and epsilon 1J1 would be 0.
Exactly.
No matter what J is.
Perfect. And then we would have epsilon 2, J1, A2, B, J. And the only number that would work here that doesn't give us a repeat would be 3. So this has to be epsilon 2, 3, 1, A2, B3. And then
we would have forcibly epsilon 3, 2, 1.
Yes. So 3, J, 1, A, 3, j. The only one that would work here is 2. So this also has to be epsilon 3, 2, 1, a 3, b 2. But I had mentioned that there's two sums here. So this was the sum of epsilon
Would the other sum be varying over j instead of I? Or?
yes.
Okay.
So technically, this whole thing here was so I'll write first 3 terms.
Oh, right.
Summed over I. And now we're going to sum over j instead.
Well,
Or excuse me, I'll write,
I think these two permutations are the only ones you can get if you have k set to 1. I think we have to move on to k equals 2.
yes, that's correct.
Yeah.
I'm just making sure I'm not forgetting a constant in my formula here. I sort of misled us. There should be a 1/2 here. And the reason being is because when I go back to all of the possible permutations, we know that we've chosen k. And then for the first 3 terms here, we chose 1, 2, and 3 for I. So now if I wrote out I, of course, 1, 1 for B. Of course, we know this is 0. But I can also validly choose
I21, which
Yes,
would be the
exactly.
same as this, so you'll have to have it.
Exactly. Yes. So it's 2 plus epsilon I3, 1, A, I, B3. And then, of course, I'll erase this just to be a little bit more clear here. We know that we had said here that the only possible values of j that would work would be 3 and 2 respectively, and the same is true here. So we would need a 3 here and a 2 here. But, of course, all of these terms are in a sum. Sorry for writing a little disorganized. We know that the terms with the repeated indices go away, so it would be 0 plus epsilon 2, 3, 1, A2, B3, plus epsilon 3, 2, 1, A3, B2, plus 0, plus epsilon 3, 2, 1, A3, B2, plus epsilon 2, 3, 1, A2, B3.
And when
And
you
of course,
multiply by 1/2, the double terms will go away mysteriously.
yes, exactly. And hopefully you can see
Oh,
this is
I see. That's an even permutation, and
that's an odd one.
therefore is odd.
So, I'll write it up here. We see that A cross B 1 is equal to A2 B3 minus A3 B2, just as we predicted with the cross product and sort of alluded to with the curl, that the actual components that are corresponding to a single direction are permutated.
Right.
And that's why we use the...
Would you mind if I borrowed a chalk from here for a
Sure,
second?
go ahead.
Different color.
It doesn't matter. So, I guess I just wanted to compare this to the normal way of taking the cross product. So you have A1, B1, or I guess upper indices. No, A1, B1, A1, A2, A3, and B1, B2, B3. So summing over this diagonal gives you plus I, A2, B3, and then
Bless you.
Thank you.
trust you. And then going backwards gives you minus I, A3, B2. Wow, that's actually pretty interesting.
Yeah. So your question was about what the curl is. So I defined it down there. And if you remember from the divergence of the vector, and of course this is a vector function, so it means it's a vector field. So probably the best way to get an intuition for this would probably be electrostatics. So let's say we have some electric field that's equal to 1/4 pi epsilon naught Q over, this is just the regular formula for electric field. This is for a point charge. So,
Coulomb's law?
yes,
Oh.
or
No.
About the unit vector?
yeah. So it's the radial unit vector for polar coordinates. So,
Oh, I see. So is it just, I guess, represented by r equals 1, or?
So it's technically, if you remember the coordinate transformation from Cartesian coordinates to polar coordinates, we use the equations x equals r cosine phi, y equals r sine phi, and of course these come from basic trig. It describes a circle of radius r. But if we want to describe polar coordinates vectorially, what we need to do is we need to define a new basis. And the way that you do that is you, I'll call this E prime J. You should define it as the partial derivative of your vector in your original basis. So maybe E unprimed I with respect to I'm thinking about how I want to say this, because this is going to be a Jacobian. Your coordinates in the polar basis, and I'll denote it like this, is going to be this matrix of partial derivatives from Ex to Ey, where the components of this are going to be the different derivatives of x and y. So J is going to equal this matrix partial x, partial r, partial y, partial r. This will be partial x, partial phi, partial y, partial phi.
Oh, wait a second. I don't know. That feels a little similar to the rotation matrix.
It is. It's just a rotation matrix.
Okay.
So doing the actual algebra, you'll see that E r is going to equal partial x, partial r, E x, partial y, partial r, E y, and there's this implication that we can think of basis vectors as derivatives. So using, just recalling the multivariable chain rule, E dr equals partial x, partial r, if r is a function of x and y, which we know that it is because we say that, going the other way around here, r is the square root of the quantity x squared plus y squared, and phi would be the arctangent of y over x. So we have this going on, kind of implicitly. And this actually defines vectors as derivatives, and they're also called one-forms. But that's kind of like a later thing for some more tensorial stuff. But the point where I'm going with this is when we define a point in Euclidean space in R2, we have, I'll use a different color actually. actually. If we drew out our basis vectors, you have x hat and y hat. Basis vectors tell you how to count what your unit of your coordinate system is in a roundabout sense. So this is 1 unit of x. So when we define a vector, the vector 2, 3 is actually equal to 2 x hat plus 3 y hat. So it's 2x units and 3y units. So it's a way to think about it. But if we want to use a different coordinate system for the sake of convenience, now we're looking at a vector r equals r phi, where now our unit vectors are r hat and phi hat. So now these tell us how to go in the phi hat direction and the r hat direction. So this is phi, this is the length r for the radius. But something that's important to keep track of here is, as you rotate this vector around for different angles of phi, this r hat unit vector is going to get translated around the unit circle. So by definition, this isn't a constant unit vector at every point in space the way x hat and y hat are. I can take x hat and y hat, and this square of area 1 is going to be the same no matter where I put it. Now that's kind of not necessarily true here. Of course, this area would be the same because basis vectors and coordinate transformations should always preserve distance, but now we're measuring distance in a different way. But going back to curl, so that's just what this guy is. Basically, it just means that you're pointing radially outward at every point phi.
Yep. Or radially inward if the charge is inverted.
Yes. So I'm going to assume we have a negative charge. So I'm going to center it at the origin here, Q. And if I drew this vector field, and looking at this is just some constant divided by r squared r hat, where we're taking the source of our vector field to be at the center. Of course, we know that this Q is in here, but this is just an inverse square law. So if we drew the vector at each point geometrically, we would see that if we wanted to draw the areas proportionally to which point they're at, that they would die out as you get further and further out. So these arrows would get smaller and smaller. So basically, as you go out to infinity, the electric field dies out.
And that's what the R component is for, right?
Yes.
Q
So
over
only
R
go.
squared.
Yes, exactly.
Right.
But now, if we wanted to take the divergence of E, divergence would just be, so now you would have to define your nabla in a different coordinate system. You would have to perform a coordinate change on this because we previously defined it in the Cartesian basis. But this is also equal to, I believe, I think basically when you do have, we use the Jacobian matrix to find the transformation of partial derivatives, and then you normalize. You'll get some constants times like partial r, and some other constant times partial phi. I believe it's 1 over r and 1.
All right. So it might be a dumb way to think about it, but I guess with that, guess I'll use this diagram that you.
Yeah, sure.
It feels a little too small though, so
Yeah,
guess
go ahead.
I'll draw something a little bigger. So, for example, a vector field similar to the one that you just drew, versus a vector field with just a point charge. With all these arrows pointing outwards. So I guess this might be a dumb way of going about it, but I guess if you have that point where the vector is originating from, then the position vector then has a very large angle with the vector field at that point, while and with this point charge, the position vector is in the same direction. as the vector field. I don't know. That's just my way of looking at it.
Yeah. Yeah, actually, I would say that's not a bad way of thinking about it, because what you're doing is you're saying there's no orthogonality going on between some other. Of course, it only works for vector fields that look like they're circular in some way, because you can have a vector field that does something like this. You know, it's maybe just like random, and then you have like some straight lines going through here. You know, it can look random and still have curl to it. It'll look a little less intuitive maybe than what it would for, say, a magnetic field around a wire. But yeah, I would say for the sake of argument, that's okay. Yeah. So one last thing to highlight is just as the curl of E, because E in this example here, E is going along a straight direction. So the curl, you can use like the right-hand rule and say if I point my thumb in the direction of E, my fingers will curl in the direction of the cross product. That's why B is circular here. But now looking at the cross product of B, we should be able to go the other way around. It should be that we should get intuitively and geometrically that the curl of B goes back in the direction of E and the current flow. And of course, B is flowing this way. So if I point my thumb, maybe like right here, if I point my thumb down, and my fingers will start to curl around it like that, but my fingers are still pointing like that way, if you see what I mean. So you see that the curl maps us back into the direction of where we started with the electric field. So.
I love the right-hand rule.
Any more questions about anything regarding the curl? I can get to.
Not really. I guess I have a more intuitive definition of it now.
Good.
Great.
So now a couple of Maxwell's equations again. So we have the divergence of the magnetic field equaling 0. And hopefully you saw that in a lot of common examples, like the case of a charge moving through a thin wire, that the magnetic field always looks circular. It's always going around the wire in a circular path, so to speak. So there's never any,
right.
there's no such thing as a magnetic charge. There's no magnetic sources as far as we know. So
it's as if, I guess, it's completely orthogonal to the position vector, or?
Yeah, if you took the position vector to be from the wire to whatever.
From the wire to the point in the magnetic field.
Yeah. So we have this equation, and then we have the curl equations that I showed you as well. Curl of E equals negative partial T B, and I forgot the name when I did this in our last section, but the Helmholtz theorem. It's something that would be nice to read up on. Griffiths has a good, I think it has an appendix on it and a section on it in the first chapter. But it says that if the divergence of some vector, let's call it F, is 0, then there must exist some other vector G such that F can be taken to be the curl of G, and the proof would just be because the divergence of the curl of a vector is always 0. That's just a math identity. You can prove that by writing out the definition of nabla for, maybe a Cartesian basis for like general components. But what that means is this implies that there should exist some vector, let's call it A, such that the curl of A equals B. And that's because if we plug that in, we will be taking the divergence of the curl of something. And then of course A has three components, an X, Y, and Z component, just the same way that B does. And this is kind of, the Helmholtz theorem also it also tells you why the divergence, or excuse me, the gradient of some scalar function is equal to E. Of course, in electricity and magnetism, we take the convention to make this the voltage or the potential, the electric potential, and use that negative sign. But this is because of Gauss's law. The divergence of E in a region where there's no charge is 0. I'll write over here for charge density equal to 0. So basically, if you remember Gauss's law, you have this closed loop, or this closed surface integral over some Gaussian surface S. That's also, I believe it's equal to the charge. But if you take the surface to be around an area where there's no charge, this will equal 0, and then you can start to formulate this notion of potential.
What's the surface area of a vector field again? No, the surface integral, sorry.
It's so if you, let's say you have some, because this is also it's also a flux integral. So if you have some, let's say, sphere with a charge at the center, and let's say it's like a positive charge, and the electric field is coming out of the sphere. We drew its vector field. So like this. If the surface has, if the sphere has a surface of area A, then if you integrate the electric field, because these are all vectors, of course, if you integrate the electric field times dA vector, dA vector is defined as the normal vector times an area element over the surface. This circle is used to denote the fact that this surface itself is closed. This normal vector is a vector that's normal to it radially at every point, regardless of the direction of whatever vector field is like kind of piercing it per se. Of course, in the case of a source charge, since everything's radially outward, so in this case, E would be equal to some radial function, or the magnitude would be in the radial direction. So this is some function that's not necessarily constant. Of course, we know it's not constant because it has to go to 0 as you go infinitely far outwards. But it would be in the radial direction, and R dot n would be 1 for a sphere. So basically, what happens is you're integrating the electric field vectors dotted with these normal vectors, and if you remember, the dot product is the measure of how in the same direction two vectors are. So the reason this is the flux is because it's a measure of how much of the field is coming out of the surface. And that's part of the reason we need this closed. And that's proportional to 1 over epsilon naught of the charge enclosed. Of course, in this case, that would be Q. And this comes from, so there's the integral forms of Gauss's law, of Maxwell's equations, and the differential forms, so to speak. So this is the same thing as saying the divergence of E has to be equal to charge density over epsilon naught.
Right, and that's because rho is Q over V, so I guess multiplying by V on both sides makes those two a little bit more similar?
Yeah, so if you divided by, well, first off, you could integrate this over a volume over this, this would be equal to the integral of rho epsilon naught over volume, and rho is defined as charge per volume. Of course, when you sum up the whole volume, what will happen is what you'll be left with is, and this is actually just the definition of charge. If you integrate your charge density over where it's defined, you'll have some amount of enclosed charge. So this is the same volume, of course. This will be 1 over epsilon because this is just a constant, and then you'd be left with the charge enclosed in volume V. But by the divergence theorem, this integral is equivalent to a closed surface integral of this vector function dotted into the surface normal vectors, which is just defined as this over the surface that encloses the volume. So this is a vector calculus identity that you usually talk about towards the end of the course and all of that. But yeah, so back to the Helmholtz theorem. I was just trying to highlight that for the case of a static field, you can always define E as the gradient of some other scalar function, known as the electric potential. For the Helmholtz theorems generally, this is the case of electrostatics, of course, but the Helmholtz theorem comes in saying that if there exists phi such that the gradient of phi equals E, the curl of the gradient of any function ever is also always 0. So here it was because of the divergence, here it was because we had the gradient of something going on. It's not necessarily because there's a 0 charge density. But the actual full Helmholtz theorem says that you can define a vector as something that has both a divergenceless and a curlless component. So basically I could write either of these vectors as a sum of the curl of some other vector plus the gradient of a scalar function, but when you look at the closed path integrals and surface integrals of the E and B fields, we find that they have different behavior. Of course they have to, because this is a consequence of flowing charges. E is a consequence of the charges themselves. So it turns out that there is no vector potential formulation for the electric field, and the vice versa for a scalar potential formulation of the B field. That's something that would probably be good to read up on Griffiths. But where I'm going with this is, that we just defined the B field as the curl of A. So looking at this, if we wrote out every component of E and lined it up with the partial derivative of the respective components of B, you'd find that you have a differential equation. Of course, it's not necessarily the most solvable using like regular methods of differential equations, but what we can do is we can assert that there must exist some null solution or homogeneous solution and non-homogeneous solution. The homogeneous solution would be the case in differential equations. This is the case where would just be the curl of E equaling 0. Of course, that's the electrostatic case. this should also be a solution. So, in this case, we actually already know it. It's just the regular vector potential of E. So we know that one solution of curl B equaling negative TB for E is E equals this scalar gradient, or the gradient of the scalar function, the voltage, the electric potential. So this is one solution. But what about for non-homogeneous case? So we just said that E equals the curl of A. So for the partial derivative of B, something that's nice about differential operators is that they can be applied, at least with partial derivatives, when you're using the nabla. What happens is this actually just gets applied only to the A. That's just a way of how we define things here. Because what would happen is when you carry out the determinant, each component of A gets the partial derivatives. So you'll have these spatial derivatives of everything with the partial derivatives, and if it's a nice enough behaving function, of course, you should be able to exchange the order of derivatives. But this implies that the curl of E equaling the negative partial derivative of B equals the negative gradient cross product partial T A. So we have the curl of some vector function on this side, we have the curl of some vector function on this side. This negative can be distributed just to here, so I can actually write this even more explicitly and just say the curl of the quantity of negative partial A partial T is this. This implies that E must also equal, and this is technically the non-homogeneous solution to our differential equation, partial A partial T. So, all of this implies that given the electric potential phi and vector potential A, we can formulate Maxwell's equations just the same as phi and A describe the E and B fields just as well. So, explicitly, of course, the sum of solutions should also be a solution. So, what we've derived is that E can be formulated as the negative gradient of the electric potential plus the negative partial derivative of A, which is just minus partial A partial T, and then we said from the get-go that B equals the curl of this vector function as well. So, using this, what we can do is now going to relativity, we can define the 4 vector A mu. This is defined as the 4 potential. And this equals, I'm going to assume natural units, so assume C equals 1. This equals phi a vector. Of course, this is 3 components, so you have the 4 components to make it a 4 vector. Do you see how I've gotten this so far? Cool. So this is the basis of how we formulate electrodynamics covariantly, an index notation such that we can make things Lorentz invariant. So I want to show you, that's just from the convention of the metric. And Dr. Verbershot likes to use the signature plus, minus, minus, minus. Do you know where that comes from?
No. I don't know. I feel like he always uses the minus, plus, plus, plus. I don't know. Minus 1.
He mentioned that he sorry.
Minus 1, 1, 1, 1.
Yeah, so you can formulate special relativity the same way. In his notes, I remember him using this for the majority of our stuff. You can also, because it's equivalent, right?
Just the sign change.
Yeah, exactly, and that comes from the space-time interval that defines Minkowski space.
Yeah.
Okay, just wanted to make sure you see that. So I'll just put a parentheses here for this, depending on signature. And then also, if you didn't assume Gaussian units, taking advantage of them is a good way to show you the 2 wave equations that you can get on each of these quantities to formulate this as a 4 vector that's explicitly proportional to the 4 current. Because so I'm going to show you that the 4 current itself is Lorentz invariant by definition. But there's usually a factor of 1 over c somewhere floating around when you're not using natural units. But so recall that J mu is equal to rho, so the charge density times the charge density and the spatial components are the current density ones. Of course, current density is only in spatial directions, but we know this is Lorentz invariant because by definition, we have, so if you consider a infinitesimal piece of charge, it's the charge density times the volume it's in. So if you expand this to the language of 4 vectors for each 4 vector x, for x mu being the coordinates that describe each point in space-time, what you can do is you can say that dq times some infinitesimal shift in the coordinates, it's equal to rho dv, and we can use chain rule to say that the time derivative of the 4 vector times the differential of the 4 vectors, dt, that these are equivalent. All I've done is I use chain rule to make these dt's be here to make it equivalent to a regular differential, and then I just multiplied this by dx mu. Does that make sense? Cool. So we have this velocity term. It's not for velocity because this isn't the proper time, but what I want to do is I want to bring this dt over here. So what I'm going to do is, of course, this isn't time dependent, but x mu, each of the coordinates in relativity can be. So dq dx mu dt is equal to rho dv dx mu dt. I could have just said, let's just consider multiplying both sides of this by dx mu dt, But what I want to highlight is that this is essentially like a 4-vector version of the continuity equation for the case of charge. Because remember that current is specifically defined as rho times velocity. This comes from electrodynamics. So what happens now is I can say, since x mu equals, I'll use dx mu, since this is equals dt, dx, dy, dz, dx mu dt, and then there's this factor of c in there. This equals c, and I'll use x dot, y dot, z dot, the dot notation for.
You said c equals to 1 earlier, right?
Yeah, right now I'm suspending that for the time being, so technically
okay.
I need that. But when I plug this in here, what happens is rho v dx mu dt equals the volume times c rho, x dot rho, y dot rho, z dot rho. These are just the components of the regular current density. Excuse me, the current itself. And this is equal to something that's proportional to dq dx mu dt. So to highlight this a little bit better, it's equal to some charge, some chunk of charge times the time derivative of x mu. And the reason this is important is because we know x mu is Lorentz invariant. Each point in space-time, so for coordinate transformation, x mu getting mapped to x mu, I'll write it like this, prime function, the original coordinates. The map itself is simply the Lorentz transformation L mu prime, such that this equals, wrong notch there. And you see that we have this contraction of indices right there. I could have written it like this just to kind of not use mu twice, but the contraction of indices leads us to that. And the reason I wrote this is because that's how coordinate transformations work. And that's how, if you wanted to construct L mu prime v or x prime mu with the Jacobians, you would use your equations of the new coordinates in terms of the old ones. That's just regular coordinate transformation. So, but the important thing is this is equal to the volume times forecurrent, and the forecurrent is proportional to something Lorentz invariant, which means this must be Lorentz invariant. Do you see that?
Mm-hmm.
Good. So now what I'm going to do, going back to electrodynamics, is I'm going to prove that this has to also be related to J mu. Because all I've done is I've said, let's just take phi and the vector potential, put them together, and you have something that has 4 components, and we're going to call it a 4-vector. But that's not really satisfying, and you really don't know if it's. I mean, of course, I've told you it's Lorentz invariant, but it's good to see that it truly is Lorentz invariant. So. I'll touch on them just to kind of show you where it comes from. The Lorentz invariance of the 4 potential. So I want to be careful of what conventions I'm taking here with the units, but so for the divergence, we said that Maxwell tells us that it's simply this guy. And then this is just a formula I'm going to just state. The cross product of the the curl of the curl of a vector can be written as the gradient of the divergence of that vector minus its Laplacian. And now in this case, this is simply curl of B, which is this equation right here. So it turns out that this is going to be equal to exactly what I've listed for the vector potential A.
John.
And so now what I'm going to do is I'm going to insert E into here. So this is equal to mu naught J plus mu naught epsilon naught partial T. I'm going to factor out this negative sign because remember there's this relative negative sign between.
We're referencing this, right?
Yes, exactly.
Okay.
So we have the partial derivative of gradient of phi plus the time derivative of A, and what this implies is if I rearrange the terms, what I can do is the time derivative of the gradient of phi and this term on one side. So basically I'm going to add this over and then add this over. So I'll have the gradient of the divergence of A plus mu naught epsilon naught gradient of this, which is how I wrote it over there. Partial derivative of the gradient of phi. This is equal to the Laplacian of A minus mu naught epsilon naught, and what I've done is I've distributed this partial T now. It's right here. This is the second order time derivative of the vector potential, and then we have that term mu naught J still there. What I can do now is I can factor out a nabla. And of course, the reason I can exchange these derivatives is because these functions had better be well defined such that we can anyways. So I now have that the gradient, the divergence of A, plus mu naught epsilon naught partial T phi equals what I have there. And so now, now here's where things get a bit tricky. So there's an implicit symmetry about these equations here. And this is getting into the gauge theory stuff. So if I shift A to A prime being equal to the original vector potential plus some other vector, let's just call it alpha for right now, and phi to phi prime being equal to phi plus some other function beta. And we know that this has to be scalar and this has to be vector because these guys are scalar and vector respectively. Any questions so far?
Not really. I think I'll end it a little sooner, just so I can understand everything and we don't have to redo something next time.
Yeah, sure, I understand. In that case, B as the curl of A, and now what I want to do is, if I've perturbed A to A plus some other vector, phi to phi plus some other scalar function, let's consider now B being equal to these shifted functions here. So now this would be A prime, which is equal to the curl of A plus alpha. These have to describe the same magnetic and electric fields if these terms have some symmetry about them, such that A prime and phi prime do in fact describe the same fields. So there has to be a condition that we derive here. So the curl distributes, we get the curl of A, which is our original magnetic field, plus the curl of alpha. The only way in which this is truly equivalent to B is if the curl of alpha equals 0. This implies that there exists some function lambda that's scalar that we can write alpha as the gradient of. So, if alpha is the gradient of some other function lambda, we can choose this to be a gauge symmetry of our equations. So the vector potential is gauge invariant up to some alpha such that it's equal to the gradient of lambda. And I'm going to show you what we can make lambda specifically be to give us some equations on A and phi such that I can prove that it's Lorentz invariant. So now for E, it's a function of both phi and A. We need to figure out how to make E also be equivalent to the original. We need to make phi prime and A prime describe the same field. So, subbing in what we have for phi prime and A prime, we have the gradient of phi plus beta plus partial t of A plus alpha, but we already proved that alpha should be this gradient right here. And so now, writing it all out, this is negative phi plus the gradient of beta plus partial TA plus the gradient of lambda. And so if I want to, I can combine beta and lambda here to be negative, so I'm going to write it like the original E field, so negative of the quantity of the gradient of phi plus partial TA minus the gradient of beta plus lambda. I've simply factored out this Navier symbol between them. And what this implies is this term should be equal to 0. So it had better be true that the gradient of B is equal to what have I forgotten here? Derivative of the gradient of lambda. So exchanging the derivatives makes this the gradient of this quantity here. So it had better be true that this equation is satisfied, which is partial derivative of lambda is satisfied, which is also equal to negative partial t alpha. So now we've related beta and alpha to each other such that we can get these gauge invariant quantities to describe the same E and B fields. So there's something to note about this equation here. If the gradient of some function f, that's a function of position and time, is equal to 0, since these are position partial derivatives, this implies f must only be time dependent. Hopefully that's pretty clear. If you take the gradient of something, if you take the position derivatives of something and they're zero, well, it just means that the only thing it could depend on is time. So what that means is for this equation here equaling 0, what I can do is I can say that beta equals negative partial t of lambda plus some other function that's a function of t, because the gradient of this be equal to 0. Of course, this is assuming that this is time dependent too. So what I can do now is I can say, well, let's just choose some other lambda, maybe lambda prime, that's equal to the original lambda minus kt to absorb this together. So of course, just a little sanity check, negative partial t lambda prime equals negative partial t lambda plus k of t. And what I'm doing here is I'm choosing a way to describe beta such that it's all in terms of the same thing here, which would be lambda. So I can simply just relabel this lambda prime as v lambda. So now what I can do is I can see the explicit equations on A or gauge invariant is this. And for phi, it is this, where this lambda satisfies this equation. And what I've done is I've just relabeled the lambda prime as v lambda. It's just a little caveat to keep track of, but it's an important for what I'm trying to show. So now what I've done is what I want to encapsulate the Lorentz force and Coulomb's law. And if you do that, since that's describing, since the case of the Lorentz force, it describes electrodynamics, what I can do is I can make the force potential proportional to the force current. That proves that it's Lorentz invariant. So in magnetostatics, divergence of A is equal to 0, which implies that the Laplacian of E equals, the divergence of E equals the Laplacian of phi. And this implies for the equations that I had derived earlier on A and phi down there with the, so these equations here, it implies that if you substitute this in, you get rid of a term. And those equations simply reduce to the Laplacian of A minus mu naught epsilon naught partial t A equals negative mu naught j plus mu naught epsilon naught gradient partial t phi. This is what's known as the Coulomb gauge. And the information on lambda is encapsulated in right here. So you choose this such that the divergence of A is 0. And if you do that, what you've done is you've described magnetostatics, which would describe Coulomb's law. And that, of course, and that Coulomb's law explicitly comes from this equation. But for the Lorentz gauge, what we do is we choose the divergence of A, and hopefully you can kind of see this freedom of choosing lambda such that or those other vectors and functions over there, alpha and beta, such that they can be written in terms of this lambda here. What it does is it allows us to control the divergence of A, or we can choose it such that we're controlling the divergence of A. Because the divergence of A is crucial to how we define the electric and magnetic fields, depending on if charges are moving or not. So if we choose this to be true, this equation right here, then that equation down there becomes Laplacian of A. I'm almost done here. Laplacian of A minus mu naught epsilon naught partial t squared A equals negative mu naught J. But that also implies that the Laplacian of phi minus mu naught epsilon naught partial d squared phi dt squared equals to -1 over epsilon naught phi. And if you remember the D'Alembert operator, or the wave equation operator, it equals this. So basically, if I put some function right there, these differential operators get applied to it. That's exactly the structure we have right here. So we get these wave equations on A and phi. Now, we're right at the crutch of what I'm trying to prove. So if we do what's called choosing Gaussian units, so Gaussian units are just another way of redefining our constants.
So mu naught and E naught are 0 now? Oh, 1, sorry.
Gaussian units are a bit different than natural units. What they do is they specifically choose 1 over epsilon naught to be equal to 4 pi. And if you remember, 1 over mu naught epsilon naught equals 1 over c squared. If I sub in 4 pi here, I get 4 pi over mu naught equals 1 over c squared, which implies that mu naught equals 4 pi over c squared. I'm writing a little sloppy here, sorry. But what happens now is this equation becomes -4 pi over c squared So this is now a column vector. This is equal to 4 pi over
C squared?
yeah, c squared, but I'm trying to figure out what do I do here with the is equal to -4 pi over c 4 current. But this right here is equal to, this is how we define the D'Alembert operator. My indices wrong. And since J mu naught is Lorentz invariant, it must be true. That A mu naught is too. So, this is why we're allowed to use A mu naught to define electrodynamics covariantly. So, if you remember the field tensor, is given by this guy. And this is a 4x4 matrix that encapsulates all of electrodynamics in a single matrix. So there's a way to see how this definition falls about from some probably much more complicated physics, but this is one of those things that for the sake of the course, at least at an advanced undergraduate level or like first year graduate level, I would imagine, you would probably need like a quantum field theory course or a harder GR course to kind of explicitly show how to make this come about from something completely unrelated. Basically a derivation of the definition. The form of this also defines what's called a wedge product. Dr. Verbeschott doesn't go over that, it would appear as far as I know either, but they're also related to one forms and covariant vectors and so on. But
I've heard
yeah.
of that. Yeah, it's popped up once or twice in my topology class. Might not be the same wedge product, but
it probably is. Yeah.
there are not that many things in math named wedge products, are there?
Yeah. I would imagine not. But,
The one that looks like this with
Mhm.
the arrow symbol? Yeah.
Yeah, it's very related to tensor calculus as well, or at least differential